Shall we start? Okay, so last time we started exploring the general structure of a two-dimensional conformal field theory. In particular, we talked about the stress tensor and the central charge. So the central charge is a very important quantity that characterizes a system, and we saw a few applications at the end of the lecture. So there is much more to say about the general structures of a conformal field theory, but I'll do that. So I'll talk a bit more about that tomorrow. But for today, I decided to focus a little bit on more applications to statistical physics and condensed matter systems. And these applications are really applications of the free boson itself again. So this is just going to be free boson and Gaussian free field. So no general conformal field theory for today. We'll do a bit more general things tomorrow again. But for today, we'll talk more about some applications of the ideas of this free boson conformal field theory or Gaussian free field. Some applications to stat-phys, to some nice problems in statistical physics and condensed matter. Okay, so there are many things that one could talk about. I selected two. So the first one that I'm going to talk about during the first hour, this is going to be critical percolation. We'll see that there are many. This is a fascinating topic in statistical physics. So we'll see that there are many things to be said about this, and some of them we can answer. Some interesting questions we can answer easily with techniques that we have learned in the second lecture mostly. And then in the second hour, I would like to talk about the effective field theory description, of one-dimensional quantum fluids. One-dimensional quantum fluids. Which is known as Luttinger liquid theory. So this is what we'll do after the break. Okay, so let's start with percolation. So what is percolation? So it's a very simple model. Very simple model defined as follows. So let's define the model. So one easy way to define it is to look at it on a triangular lattice like this. So this is a triangular lattice like that. The dual lattice is a hexagonal lattice. Let's see if I can draw it properly. Yes, like this. Okay, and so what we do is that each side of the triangular lattice we decide either to color in black or in white at random. So every side we just decide that we color it either in black or in white, like this. No interactions, nothing. Very simple. For each site we color it in black, say with probability p, and white with probability 1 minus p. Okay, what's the partition function of this object? The question, what's the partition function? Any idea? Hmm? Is it? Well, I mean, if we define the partition function as the sum over all configurations of, you know, the probability of each configuration is going to be p to the number of black sites times 1 minus p to the number of white sites. What is this? If no one knows this, I'm just gonna stop now. Hmm? Yes, it's 1, right? It's 1. So need S1. So this is going to be important because, you know, last time we talked about partition functions and the way that the central charge was popping up. In particular, we saw that on a long cylinder, the partition function was behaving in a certain special way that was involving the central charge. So what does this mean about the central charge of the system? The fact that the partition function is 1. It means, yes, it means that the central charge, whatever we are going to do, the central charge will have to be, there cannot be a non-trivial central charge here. Okay, so we'll come back to that later, but the central charge is 0, and this turns out to be important. All right, so let me just, before we discuss this more, let me just show you a few pictures, because this is a topic where if you don't see the pictures, then you don't get why it's so fascinating. So this is this model here on a rectangle, and you see each site is colored either in black or in white, and so this model becomes interesting if you start looking at the clusters, so at the geometric structures that are emerging. This is same picture on a cylinder. We'll see that it's interesting to go from the plane to the cylinder, which is something we can do with a conformal map, and this will play an important role. So if you zoom out and you know, you just so you do for instance, you do a numerical simulation with many sites, and you just decide color all the clusters and pick a different color for all the clusters. This is typically what the clusters will look like. So in particular, you know, it looks like there's some random fractal geometry that is emerging. What boundary conditions? Yes, I didn't even pay attention to this, but yes, you're right. I'll come to that in a minute. Yes, about the boundary conditions. So here, yeah, for instance, here you see what's done is that in this picture, all the sites along this boundaries are colored in black, say, and here they are all in white, which ensures that there is one big cluster touching the boundary here, and then it has a certain boundary inside the rectangle. And here again, you know, this boundary, it looks clear that it also has some fractal structure. So, you know, as physicists, we are curious, and so we would like to understand this. So it turns out there are many results on this theory, exact results that you can get. So today I'm going to show one example. So we are going to compute the fractal dimension of the percolation cluster, and we are going to get a result. So I'm not telling you what the result is yet. But there are other calculations of the same type that you can do. For instance, you can compute the fractal dimensions of this boundary, and it's a very famous result that this boundary is called the hull, the percolation hull, and it's a very famous result that the percolation hull has fractal dimension 7/4. Okay, so this we are not going to talk about this, but let me just to make the connection of with recent breakthrough in that field, in that area. There's another type of geometric questions that you can ask about percolation, which has fascinated generations of theoretical physicists, which is the so-called percolation backbone. So what you do is you look at a certain percolation cluster. Then you take 2 points, and then on that cluster, and then this cluster you view as some big graph with different connectivities that goes from one point to the other one, and it's just a general graph, so you can always decompose it into one particle irreducible components. So you do this kind of things that probably you're used to from maybe from Feynman diagram type of techniques, but you can do it. It's just graph theory, so you can always do this kind of decomposition. And then the question is, what's the fractal dimension of the object that remains if you remove all the single lines? So you just keep all the points that are connected by at least two different paths on the cluster. Sorry, I'm not explaining this well. Anyway, it's called the backbone. If you want to know more about this, just Google it. It's a key object that appears in percolation theory, and it has fascinated people for a very, very long time. I remember when I was a PhD student myself, John Cardy giving lectures about percolation, highlighting this as the big open question in the field of computing the fractal dimension of this object, of the percolation backbone. And it turns out it was just solved very recently. So by a group of mathematicians. So there was first a mathematics paper 2 years ago, and now they just published this PRL with the result. So the result is what it is. It's given by the solution to some weird-looking equation like this, and it gives a certain fractal dimension, and then you can compare to numerics, and it agrees, of course, with tremendous precision. So I just wanted to flash this because I find it really fascinating. So I don't understand this, and I think it's not understood from the perspective of conformal field theory or from the perspective of this Gaussian free field. So if some of you are interested in conformal field theory and want to make a useful contribution to that field, this is I mean, it's challenging, but it's a topic that is probably deserves probably some attention. Okay, so this is very modern research. Now we are not going to talk about this. What we are going to talk about is research from 40 years ago. But still, I want to convey the message that there are nice questions that you can ask about these random geometric phenomena that you can answer in a relatively simple way, thanks to the techniques of the Gaussian free field. So now you asked about boundary conditions. So one type of result. So let's make a very quick list of some interesting results that have been obtained about this theory, about this model. So first of all, you see, of course, if P, the probability that you have black sites, is too small, then essentially you only have a few black sites like this, and otherwise the rest of the system is completely white. If P, on the other hand, is, so this is P small, this is P large. If P is large, then the everything is covered in black with a few white sides. And what's interesting for us, for physicists, is that there's a critical point, and at this critical point you get both white and black. And in particular, if you choose this boundary in black and this boundary in black, and this one is in white, so this one is white, this one is white, this one is black, and this one is black, then you see that there are two kinds of configurations. There are configurations where there's a cluster that crosses in this direction, and there are configurations where there's no crossing cluster. And you can ask, what is the probability that that this happens? What is the probability that there's a percolating cluster? And it turns out it's a question that you can answer using conformal field theory, because this happens to be so critical percolation is conformally invariant. So you could ask the same question on any other type of surface, like if you color this in black, these sides along the boundary in black here, those in white. And you ask what is the probability that there's a cluster that goes from this side to this side. So if this is some domain U, the answer will be the same as in the rectangle or as in the upper half plane if you do the right conformal map. So you can use the technology of conformal mappings to answer this kind of questions. And the first person who computed this crossing probability was John Cardy. But this is really a topic with a glorious history, with many famous scientists associated to that. So I think the first maybe was Langlands. It's the same Langlands as from the Langlands program in mathematics. So they were doing numerics, and they found that it looked like it was conformally invariant. So then they asked the question to John Cardy. So Cardy came up with his formula with some sort of genius intuition of how to connect this to a correlation function in conformal field theory. And then the topic was picked up by mathematicians, and I mean, there have been several Fields Medals for this kind of topics. So one very big name was Schramm, who came up with the Schramm-Loewner evolution, and then Smirnov, who proved that percolation was conformally invariant and got the Fields Medal for it, and so on. So it's such a simple model, but there are so many interesting things to say about it that it's really a topic that has attracted the attention of some of the greatest minds in the past 50 years. Okay, but today we're not going to be so ambitious. So what I want to do is to compute the fractal dimension of the percolation cluster. Okay, that's one easy question. That's one easy question that we can answer with the techniques that we have seen so far. So to do this, we need to first find a mapping from percolation, from our percolation model to a discrete Haidt field, to a discrete Haidt model, to a discrete Haidt model. So how does this work? So we have our lattice like this. So we have our sites that are colored, and then we observe that we can draw the contours of the clusters, and the contours of the clusters are closed loops, right? So for instance, here, the could draw this. This would be a closed loop. Now, closed loops somehow are intimately related to models of fluctuating heights, because if you have a model, if you have a height model in 2 dimensions, so you have a certain height field h of x, so at each point you have a certain height h. Then what you can do is that you can draw the contour lines of this height field. Okay, so you can draw the contour lines, and the contour lines are going to look typically like this, things like this. But contour lines have an orientation, right? Because you need to specify whether the height increases or decreases as you go through one of the contour lines. So there are also loops in the Gaussian free field, for instance, which is a model for a fluctuating height field h of x. We have loops, but these loops are oriented. While in percolation here, the loops are not oriented. So we need to find a trick in order to orient them. And in doing so, we also want to keep the locality of the model. So the trick to do that is to replace each closed loop, like this one, for instance, is to replace it by 2 configurations, by a sum. So each loop configuration we replace by a sum of 2 loop configurations. And each loop can be oriented then clockwise or anti-clockwise. Okay, and in the partition function, each closed loop is going to have, so on the percolation side, this is going to have a weight, all of them are going to have equal weight 1. If we, I mean, normalized by the partition function, but so this is going to have a weight 1, and those, so this is going to have a weight, let's say for W clock, some weight W clockwise, and here some other weight W anti-clockwise. So that the total weight of each loop will be this plus this. So this plus this, we want to be equal to 1. So the idea is to, okay, so if we look at our honeycomb lattice, hexagonal lattice, and we look at one vertex, we see that if there's a loop going through this vertex, then there are several possible configurations. One is, for instance, our oriented loop goes this way, or our oriented loop goes that way, or could go that way, but then going this direction, and so on. And so what we do is that for each of them, we give some weight. Each of these possible vertices, we give some weight. And the weight is just a phase. Okay, so for this one, we would give some weight e to the minus I lambda over 6, where lambda is to be, we will determine lambda shortly. So every time we turn a little bit to the right, we give some weight, we give this phase, and if we turn to the left instead, then we give the opposite phase, so complex conjugate. Okay? Now you can check that for closed loops, for any type of closed loop, so for any type of closed loop, the total angle by which you have turned has to be 2 pi. And so a closed loop oriented oriented clockwise will pick up total weight e to the minus I lambda. That was the reason for putting these factors 1/6 here. And a loop oriented counterclockwise will pick a weight e to the I lambda. So that the total weight of this configuration, total weight of a loop after we have traced over orientations, this gives us a loop that has no orientation anymore, and the weight of this thing should be 1. So this weight should be 1, and so this tells us that we should pick lambda equals pi over 3. So that 2 cosine lambda is 1. Okay, so that's the first ingredient. Now we want to think of these oriented loops as contour lines of our discrete height field, and we decide, so the rule to map now a configuration of oriented loops to a configuration of a discrete height is that h jumps by plus or minus, by some amount plus or minus a every time we cross, when we cross an oriented loop, and the plus or minus depends on the orientation. Okay, so for instance, on this picture, I could decide that the height here, let's say we fix it to 0, and then every time I cross a counterclockwise loop, I increase the height by plus a, and every time I cross a counterclockwise loop, a clockwise loop, sorry, I decrease by some amount a. Okay, so this way here I would get plus a. Maybe here I would, let's say this one is oriented in the same direction, so then I would get 2a, and so on. So we see that the discrete field that we get in this way, we get this gives us a discrete scalar field that is defined on the points of the triangular lattice, and this discrete height field takes values in integers times a, times this parameter a, and a will be fixed shortly. Any questions at this point? No? Okay, so now comes the physics intuition. So far, everything was just playing with definitions and completely transparent. But now comes the physics intuition. So the physics intuition is that. So the physics intuition is that the fluctuations, the large-scale fluctuations of this height field, large-scale fluctuations of H, of this discrete H field, H, are captured, will be captured by a GFF. But the GFF that last time I normalized in this way, so the action, remember, was normalized in this way, and I'm going to use the same convention now. It was gradient of h squared d2x. Okay, and you know, I mean, this is an assumption. It makes sense from a physics point of view. You know, we expect, I mean, we saw from the picture from the pictures that everything looked nicely scale invariant and conformal invariant. So why not? It looks consistent. Okay, so there's one more. So we are almost there, and we are almost ready to compute this fractal dimension. But there's one more ingredient that we need, which is something that in the literature is called the background charge. I'm not really going to use this vocabulary, but it's good to know that it's there. So background charge. And to do this, one standard way to do is to look at what happens on the long cylinder. So why the long cylinder? Because last time we discussed partition function of long cylinders. So now we look at percolation, our percolation model on a long cylinder like this. So we used same notations as last time. So capital L is the length of the cylinder, little l is the circumference. Let's say that this is at position minus L over 2, and this is at position plus L over 2. We have capital L much larger than little l. And we have our percolating model, so we have our oriented loops. After we've done this thing, we have our oriented loops that live here. So that defines our height model on this cylinder. Okay, but now you see, now there is a big problem. What's the big problem? Well, so last time we saw that the partition function of this object, so the Gaussian free field is a conformal field theory, and we saw that the partition function on a long cylinder, we saw that this was going as always as exponential pi c over 6 capital L divided by little l. Okay? Vincenzo. Okay. Right? This is what we saw last time. On the other hand, as I said when we started, just when we defined the model, the partition function should be 1. Shouldn't scale with capital L. And for the Gaussian free field, sorry, we saw last time that, of course, for the Gaussian free field, central charge is 1. So the central charge is 1, it is not 0. Okay, so there's a problem here, and we need to cure that problem before we can go on. So what's the problem? The problem is that the mapping was not quite complete for the following reason. So if you think of along this very long cylinder, there are these nice small loops, but there are also loops that can go around. Also loops that can go around the cylinder, that can go in both directions. And if you think of what happens to these loops that go around the cylinder, well, these loops do not turn by an angle 2 pi, right? Because typically, I mean, let's say we have a very small lattice like this, you know, and we take periodic boundary conditions here. So we just identify this with this side with this side, right? So this here is identified with this side. So this we have periodic boundary conditions in that direction. Now, if we think of what happens to a loop that would, for instance, do this, that would go as this, in total, it doesn't pick an angle 2 pi, it picks an angle 0. And because of this, these loops pick up a weight 2 and not 1. So these non-contractible loops So these non-contractible loops pick up the wrong weight. And we need to correct for this before we can apply these ideas to compute the fractal dimension. Any questions at this point, or no? Hmm? Okay, so the problem that we are facing now is that these non-contractible loops do not have the correct weight. So they have weight 2 in the partition function, and they should have the same weight as all the other loops, because nothing should distinguish them. So they should have weight 1. Okay. But it turns out this can be cured relatively easily, because if you think in terms of the height field, in terms of the height configuration, you can easily count the number of non-contractible loops that are oriented in the same way. So let's say they are all oriented in the upper direction. Then it's easy to count them, because every time you jump across one of them, you pick up the height field jumps by plus a. Right? You add a factor a. You add you pick up an additional a. So the total number of such oriented loops, non-contractible loops, if we assume for a second that they are all oriented in the same direction, this is just going to be given by h at plus L over 2, let's say, so far away on the right of the cylinder, minus h at minus L over 2 divided by a. Okay, so this is the number of non-contractible loops. This is the number of non-contractible loops with the same and with the same orientations. Going up, say, same orientation going up. Okay. But this you can correct easily then, because what you can do, instead of computing the partition function of the free field on the cylinder, you can just modify a little bit the partition function and say that z, so the partition function for percolation, you can just replace it by, so you say that it's the partition function of the GFF times a correlation function, and the correlation function you just take as exponential I lambda times this number of non-contractible loops. Sorry. Okay, this correlation function, and then ultimately we just take, so every such non-contractible loop, if we do this, is going to pick up a weight. So these non-contractible loops of non-contractible loop is now, because of this factor, will be e to the I lambda plus e to the minus I lambda. And so in the end, we just have to take lambda equals pi over 3 as well, so that the weight will be 1. Okay? But now, because the number of non-protractable loops here is given by this formula, we see that this thing is nothing but a correlation function of our favorite operators of h at one end of the cylinder divided by a, properly regularized, times this, times the same operator here. And these two operators are very far away on the cylinder. One is very far on the left, the other one is very far on the right. Okay, and that's all we need. So, because now using what we have seen so far, this is just one of these correlation functions that we have talked about so much in the second lecture. So what we see is that now the partition function of the percolation model on our infinite cylinder. So the first part, as I said, this has to go as pi c over 6 capital L over little l, because that's the partition function of a long cylinder, of the Gaussian free field on a long cylinder. And the other one, that's a correlation function that you can calculate using what we have discussed. And this is you'll do the calculation, you'll find that it goes as exponential minus lambda squared over a squared. Sorry, I forgot to factor lambda. I forgot a lambda here. Sorry about that. There's a lambda. This times 4 pi capital L over L. Okay, and so because this should be 1 in the end, so it should not scale. Okay, so there, of course, there's some global normalization. Right? There's some global normalization, but the point is that it should be the result should not scale with L, with capital L. So it should total result should not be a function of capital L over little l, and this is possible only if a squared is 24 times lambda squared. Okay, and so since we saw that lambda is pi over 3, we see that a has to be pi times square root 8 over 3. Okay? Yes? Hmm? So which formula? Well, I mean, yeah, I swept a detail under the rug. Maybe this is what's disturbing you, but I'm not going to do it now. You have to think about it yourself. But so if all the loops are oriented in the same direction, then it's easy to see that this is the result, right? Do you agree with this? Or? From the definition, we have decided that our field jumps by an amount a every time we cross a loop. Okay, then you need to think just a little. You need to convince yourself that this still goes through even when you put the other orientations. So this I will not do now, but I'm just trying to sketch the thing. Anyway, so we arrive at this. We arrive at this, that we have our discrete height model with a field that is living on integers times this quantity a, which happens to take this value for consistency. It is what it is. And now it looks like we have a description that makes sense. Because in what sense do we have a description that makes sense? In the sense that the partition function that we can compute for this model, the Gaussian free field, where we have corrected by doing something at infinity, this partition function now is 1. or say compatible with the fact that the central charge of the whole thing should be 0. Okay? I mean, there are a number of things that you need to digest. This is just this always happens the first time you're confronted with these arguments, because none of these arguments seem to make sense, and in the end you get an exact result. I think this is very much what Paul had in mind yesterday during his colloquium about results in physics being exact but not rigorous. This kind of arguments is precisely one of those. Do you agree? Hmm? Okay, so now we are almost there. We have the ingredients. Now let's talk about the fractal dimension. So fractal dimension of a cluster, of the percolation cluster. So first of all, what is the fractal dimension? So how is it defined? I mean, if we are going to talk about something and try to calculate it, we'd better have a definition. So what is the fractal dimension of the percolation cluster? How would you define it? So one thing you can do is, for instance, okay, so you fix a point on the lattice, and you declare that this point belongs to a cluster. And you look at all the other points that are connected to this one. So let's say let me just draw them as this. So, but you have many other sites that are connected to this one by some sites that are colored in black, say. And then what you can do is compute the probability, or yeah. So so the a percolation cluster is going to be the set of points, right? The percolation cluster to which this guy here belongs is going to be the set of sites. So it's the set of sites or points that are connected to this site. So it's a set of points. And now what we want to know is if we cut, I should draw it around the other point, sorry. So if we cut a certain region here around this point of size epsilon, say, with an epsilon that is not too big compared to the total system, but much bigger than the lattice spacing. So we are on a lattice, we have some lattice spacing. Let's call it A naught. So we want to look at a disk of radius epsilon, much larger than A naught. And the point is that the number of points, so the number of points in the cluster and so in the cluster and in the disk, in this disk of radius epsilon. So the number of points in that region here, we expect this to scale as epsilon over A naught times some exponent, and this exponent is the fractal dimension, df. Okay. So this is how one could define the fractal dimension. Now, how does this connect with field theory? So in the field theory, the way that we would rephrase the question of computing this exponent df in terms of a quantity that we know how to compute would be to say, well, let's this configuration with one point on the cluster that defines the cluster on which we are, and another point which somehow measures the probability that we are on the same cluster. So we can define a correlation function of an operator, say, let's call it phi. Phi is then what is living here. This is at some position x1, this is at position x2. So this correlation function phi of x1 and phi of x2, this is the probability, let's say this measures the probability that x1 and x2 are two sites on the same cluster, belong to the same cluster. Okay? And if we have this, then we see that the number of points, if we rephrase this in this language, then the number of points in that intersection, this is going to be, one way to compute it is to say that it's going to be phi at point x1, and then we can take phi at point x2 and integrate it over our disk, over the disk of radius epsilon, and take the correlation function of this thing. But we see just from dimensional analysis that this object here should scale as epsilon divided by a naught to the 2, because there's a power 2 here, minus the scaling dimension of x, which I'm going to write as capital X of phi. Okay? And so what we see is that the fractal dimension df from that argument should be ultimately given by 2 times the scaling dimension of phi, where x phi, capital X phi, is the scaling dimension of the field phi. Okay, this is the important formula here. And so what we need to do in the end then is just identify the correct field phi. The correct field phi that ensures that our 2 points belong to the same cluster. All right, so let's draw our configuration. So let's say we have a cluster that does something like this. We have our 2 points, phi with our operator phi here, phi here. Let's draw the same and we have other types of configurations like this and this. Phi, phi. Now, if we look at so this is a percolation cluster. If we look at the loop that goes around it, the loop is going to look, in that case, it's going to look like this. When they belong to the same cluster, there can be loops that go around, but they must encircle both points at the same time. While in this case, if they do not belong to the same cluster, then there can be loops that separate them. All right. So in other words, this type of configuration is allowed. This type of configuration is not allowed. Okay, so now this is a conformal field theory. We can play with conformal maps. So let's ask this question. Let's look at this question on the cylinder now. So we just conformally map this to the cylinder, and we see that this left configuration here gets mapped to a long cylinder. Let's say we have phi, the operator phi somewhere here, the operator phi somewhere here. And okay, so we can have loops inside, we can have loops that go around both. But what we cannot have, so this is allowed, these are the allowed configurations, but what is not allowed, if we look at the right picture, so what is not allowed? Well, precisely configurations where you have such non-contractible loops, right? Is it clear? I use a conformal map to the cylinder. This point here arrives here. This other point arrives here. This loop gets mapped to a non-contractible loop here. This loop gets mapped to this other non-contractible loop. This is not allowed. But we know how to forbid this kind of configurations. It's written here. It's written here. If we had written everything not with lambda, but with some number lambda prime here, lambda prime, let's call it lambda prime, lambda prime, lambda prime, then the weight of a non-contractible loop here would have been e to the I lambda prime plus e to the minus I lambda prime, that is 2 cosine lambda prime. And so if we choose lambda prime such that this is 0, in other words, lambda prime equals pi over 2, then we are killing all the configurations that do have non-contractible loops. Okay? And so, okay, so in the end, we get that phi somewhere at some position far on the left. So let's take it now at position, we send it to minus infinity or minus L over 2. L over 2, L is very large, so we take it very far away on the left, very far away on the right. And we look at this quantity now. So this, what is this? So this, by definition, is the partition function where the non-contractible loops have weight 0 divided by the partition function where the non-contractible loops have weight 1. But with what we wrote here, we see that this is a ratio of 2 correlation functions. One is with this coefficient lambda prime. And one is with so the numerator is with the coefficient lambda prime. The denominator is with the coefficient lambda okay. I should have saved some space. Sorry about this, but I'm gonna continue here. The point is that this decays as exponential minus 2 pi capital L over L times the scaling dimension of phi. This is how the scaling dimension pops out when you look at correlation functions on the cylinder for operators that are very far apart. This follows from the definitions that we gave in lectures 2 and 3. And from this formula, you can explicitly compute the scaling dimension. So the scaling dimension, using the scaling dimension of these vertex operators that we talked about last time, this is lambda prime squared minus lambda squared divided by a squared. And when you plug in, remember, lambda prime is pi over 2, lambda is pi over 3, and this a had this funny value that it was pi times square root of 8 over 3. Plug that in, you find that this is 5 over 48. That's right. Yes, yes. So you arrive at this. And then you plug that in that formula. And you find that the fractal dimension, df, of the percolation cluster is 91 over 48. Now, believe it or not, this is correct. And it's exact. It's been extensively checked by generations of physicists like 50, 40, 30 years ago. And it's been proved by mathematicians now using the modern tools of probability theory. So let's stop here for percolation. Next hour we'll do quantum liquids. Does it work? Yes. Okay, good. So, for this second hour, I would like to sketch briefly how the same techniques appear when one thinks about one-dimensional quantum liquids. So 1D quantum liquids okay, so these are called Luttinger or Tomonaga-Luttinger or Luttinger liquids. And this is a topic that is also quite old and on which you can find many references, many textbooks, many excellent textbooks. I mean, one is the one by Thierry Giamacchi, for instance. There's one that I like very much that is closer to the point of view that I'm going to take is the one by Cvelik. I really recommend this one if you like to think in terms of field theory. Anyway, there are many textbooks, and Fabian Nessler here in this school gave excellent lectures last year. So I'm not trying to compete with Fabian. Fabian went in much more details. I just want to, I would just like to try to clarify the connection between this business and the Gaussian free field or free boson that we have talked about. So to this, let's be a little bit concrete. So let's consider one model, microscopic model for a quantum gas, and I'm going to consider bosons, but you could do the same kind of discussions for fermions. Let's say, for instance, a model like this. So the Hamiltonian we take as so we have we write it in second quantization. We have a Hamiltonian like this. Let me put the factors h bar and m for a second, and then I will set h bar equals m equals 1. There's a chemical potential just so that the ground state has a finite density, and then there are some interactions between the particles. Okay, so you would write something like this: psi dagger at position y, and I should times v of x minus y, where v of x minus y is the interaction potential between two particles. Is the interaction potential, and this we don't really need to assume anything special about this interaction potential, except for the fact that it has to be local. This is very important. Short range. So it has to decay sufficiently fast. So the discussion does not apply in particular to long-range systems, or when v of xy has algebraic tails, for instance. But as long as it's sufficiently local, for instance, it decays exponentially, or it's just a delta function, then it's fine. Case of a delta function is particularly interesting. It has a name, and it's a system that is very close to my heart. That's the Lieb-Liniger model. But the discussion is more general. Okay, and sorry, I didn't say, but of course these operators are second quantized operators, so they satisfy the canonical commutation relations here. So psi dagger, and we are considering bosons again. If you wanted, you could also consider fermions. So we have these canonical commutation relations. Now, okay, so what do we do? What do we want to do? What do we want to do, and why do we want to do it? So, what do we want to do, and why? So, we are interested in the physics of the system, of this quantum gas at low temperature. That's the first assumption that we make. So we are not interested in things very far from the ground state. We are interested in the low energy physics, where there's only a small amount of excitations in the system. So we are interested on low temperature, close to the ground state. So that's the first assumption. Yes, Andrea. And what we would like to have is an effective description, so namely an effective field theory description of such a system. So I think it's standard to call it EFT description of the low energy physics of this system. So we will see that this effective field theory has to do with the free boson, with the Gaussian free field. Once we have identified the correct effective field theory description, we would like to be able to, to compute physical quantities, for instance, correlation functions, like to be able to compute correlation functions. So why correlation functions? Well, I mean, physical observables usually are related to correlation functions. And it's not the only quantity that's interesting, but very often correlation functions are the object that you need. So the important words here is low T, ground state, effective field theory, and correlation functions. Let me just give some examples of the correlation functions that we could be interested in this model. For instance, one interesting correlation function is psi dagger at position x, psi at position x prime. If you're thinking about quantum, in terms of whether or not the system has Bose-Einstein condensation, then this quantity is important, because in a true Bose-Einstein condensate, this thing would pick a non-zero value even at very long distances. That's because of phase coherence in the system. And in 1D, we'll see that this doesn't happen. So that's one example. But you could also look at higher. Sorry, I'm gonna drop the hats, right? These are operators, but let me drop the hats, because otherwise it's going to be annoying. So higher order correlation functions are also interesting. Things like this. Also, density correlation functions could also be interesting and could be measured in experiments. Things like rho x1, rho x2, where rho of x would be, rho of x is psi dagger x psi x. So if you, I mean, for instance, one of this correlation function, the way it enters in experiments, for instance, is if you measure the momentum distribution of the atoms. So you compute, if you want to know the momentum distribution of the atoms. So how is this defined? So you would define this as, let's call it n of k. This would be, just psi dagger k, psi k, where psi k is the Fourier mode. This is the Fourier mode of this operator here. Let me call it p, just to p. Because there's something else that's going to be called k, so let me call it p to avoid confusion. Right, so this is the Fourier mode of psi, which I think created some confusion in the previous lecture. That's just the Fourier mode of the field operator, right? And you compute this correlation function of and the expectation value of this quantity, and this is the momentum distribution. And it's something, okay, so if you want, it's the Fourier transform of this correlation function over there, dx1, dx2, e to the I p x1 minus x2 psi dagger x1 psi x2. And why is this interesting? Well, because it's really an observable quantity. So typically in cold atom experiments, what experimentalists do is that they can confine their atoms to very, very strongly anisotropic harmonic potentials, so that the gas is very long in the x direction here, but it's very tightly confined in the directions x and z. And then what they can do typically is that they can suddenly release the trap. So they just switch off the trap in all 3 dimensions. And then what happens is that the atoms expand. the atoms expand, so every atom goes in a different direction. But because the atoms are very, very strongly confined in the transverse y and z directions, because of Heisenberg uncertainty principle, they typically pick up a very large momentum, so very large transverse momentum. So what happens is that these atoms expand very, very fast in these transverse directions, and not so fast in the longitudinal direction, in the x direction. It's just a second. And so, because of this, very quickly they stop interacting. Very, very quickly they stop interacting. And then the expansion is just a free expansion of particles, and they expand. Each atom lives its own life, is independent of all the other atoms. It expands, and so it just propagates according to its initial momentum. And then if you take pictures of this expanding cloud, and you just integrate out these two transverse directions, you get the momentum distribution in the longitudinal direction, and this is really what they do. So there are plenty of experimental data on this, and what it typically looks like is something like this. So you have this momentum p, and if you plot n of p, typically it looks like close to the ground state anyway, it looks like this. So it has a peak. It has a peak here. So at low momentum, it goes as a power law. So this peak here, this chalk is really bad. So yeah, so this goes as 1 over p to some exponent, and this is something that they can measure. This exponent, we'll see later that there's a good reason for writing it as 1 over 2 times capital K minus 1. Okay. This is the kind of things that you can do, the kind of results that you can get from this effective field theory description. So momentum distribution is interesting, but then you can also look at correlation functions of the momentum distribution, right? So for instance, n of p times n of p1 times n of p2. This is also something you can measure, because if you repeat the experiment many times, you do statistics on the different results, and you can look at correlations. Now this would be the Fourier transform of a 4-point function, and so on. So these correlation functions in general, you want to know what they are, and because this is typically what allows you to make connections with physical quantities. Yes, you had a question? Sorry? What? No, I think that's correct. No, there's a dagger here. Yes. Is this what you mean? Yeah, thank you. Yes. All right, let me just stress one important point. Which because it's an incredible source of confusion for many references and many people, and let me just stress this. So the description that we are going to derive to this effective field theory description, it is what it is, it is an effective description at low energy, so it describes only, it's valid only at long distances, only at low energy or long distances, low energy or long distances. So in particular, you see, for instance, this quantity we get as the Fourier transform of this quantity, and this thing here, what we will derive in a second from field theory is that this goes as 1 or some constant, let's call it A, some constant that we do not know, that needs to be extracted from the concrete microscopic model. But then what we can derive from the effective theory is that this goes as 1 over distance between the 2 points. Sorry, this is x1, x2. x1, x2, to some exponent, and this exponent, okay, we'll write it later as 1 over 2k. So it's some exponent. And again, let me just stress that when we write this kind of identities, this is valid only for x1 minus x2 much larger than the UV cutoff. The UV cutoff here would be one natural length scale to consider, to take as a UV cutoff would be 1 over the density, 1 over the particle density. So the typical distance between two atoms. So this type of things this type of correlation functions that you get from the effective field theory description, they are valid only at distances much larger than the cutoff. If you're asking questions, that are about short distance physics, then you will never be able to answer them with this type of approach. Okay. So this is, I think, something that's particularly clear if you use that language. But sometimes when people present things in terms of bosonization, it's not so clear. Anyway, so let's now discuss a little bit how this works. So, okay, so let's have a look at this effective theory. So the effective field theory. So as a first crude description, we can view the liquid as a continuous. We can view our system as a continuous fluid. So we can look at our system, our gas, as a continuous fluid. As a continuous fluid, described by its density, atom density or particle density, with a density rho that is defined as psi dagger psi, rho of x, psi dagger psi. If we have a time dependence so if the fields are, so if we have some dynamics in the system, we want to add some time, so we have rho of x and t. Okay. So what we have in mind is that we have our atoms, or whatever particles, this could be electrons, as I said. We have our particles on the line. They are quantum particles, so you should think of them as having some sort of wave packets that overlap, but if we look at them at large scales, we can describe this as just by the density of that system, and so this is all described by some density rho of x like this. So we don't really care about the microscopic degrees of freedom anymore. We just look at this this continuous density field. Continuous density. Okay, and so we have this density. It's the number of particles is conserved. So this is the density associated to a conserved quantity. So there should be a current associated to it, so that the current and the density operator are satisfy the continuity equation, right? So there's an associated current. Let's call it J, and this J they satisfy the continuity equation. Okay, so now, as I stressed, so we are interested only in low energy and near the ground state. So near the ground state, what we expect is that the density, the fluctuations of the density are relatively small, so that this rho of x, now let me put back the hat just to emphasize, just to stress what is an operator and what is not. So rho, we want this to be, let's say, some background density. That's just here, that's just a number, it's not fluctuating. And plus some small fluctuation, and this one again is an operator. Okay, and there's a current. So the current is also an operator, and this current is of the same order as delta rho, not rho naught. So rho naught is much bigger than delta rho. Okay, so we have our fluid described by a density and by the associated current, and now, okay, so based on just very general principles of quantum physics, of quantum mechanics, we expect that physical observables. So physical observables, so let's call this just generically O, should be given by some, just by a path integral of some sort. So we want to think of them as coming from a path integral, where we would integrate over all configurations of rho and j, our observable O times exponential minus s, where s is some action that we don't need to know in detail. We just need to know that it exists and that it is local. With the constraint, and this constraint is very important, with the constraint that the continuity equation is satisfied. So with this constraint that dt rho plus dxj is 0. So yeah, let me just, so now so I forgot, this has time dependence, this has time dependence, this has time dependence. And here we are integrating, so it's a path integral over all configurations of rho and j in space-time, or Euclidean space-time, say, if we are interested in ground state correlations. Okay, so what we have in mind now is the Euclidean space-time. Euclidean space-time, which is two-dimensional. One direction is position x, that's the position along our fluid, like that, and then there's an imaginary time direction, tau, and by doing this path integral we can capture quantum fluctuations. Is it fine so far? Are you okay with this? Yeah. No, I mean, no. We it's better to. I mean, since this is really like a definition of the current, you want to impose it. You don't want to. You don't want to derive it from as say as a consequence of the Euler-Lagrange equation. So, I mean, actually, this is what Bernard was discussing last week. So Bernard was writing the same kind of expressions, but for classical systems, and he discussed this, right? He discussed whether or not this was going to be imposed as a constraint, or whether you want to put it inside the. I mean, you see, you could put a delta function of this right in here, and then write the delta function in the form, in the form of a Fourier transform the delta function. Then this would add like a Lagrange multiplier, and you could work with this. Yes, but it's easy. You'll see in a second that it's easier to just impose it for our purposes. Okay, so that's the key point. So we want to think of it in terms of something, yeah, path integral over this configuration of density profile and the associated current in space-time. So I have 20 minutes, right? Okay, good. So 20 minutes, we need to speed up. So okay, so the point, this constraint, as you were asking about, is the key point, and there's a simple way to solve the constraint naturally. So this constraint can be solved by introducing another field, by introducing a field. We will call it a Haidt field again, as previously, a Haidt field h of x and tau, depends on position and imaginary time tau. And this Haidt field we want to choose. So okay, for a second, let me write it with real time. And this field, we choose it such that the density is, I mean, some factor 1 over 2 pi times the derivative of h in the x direction. So here everything depends on x and t. And the current we take as minus 1 over 2 pi derivative of h in the time direction. Okay, and you see that this, then if we do this, then the constraint is automatically satisfied. Good. And then this integral, this path integral there, we can rewrite it as, just now path integral over h, configurations of h times O. O is some functional of the field h, and then minus s of h. Okay, so now you start seeing that now we have a model of there's a fluctuating Haidt field. So it starts sounding very, very similar to the Gaussian free field, or to the free boson that we've talked about. But it's not Gaussian yet. You see, I mean, this we did not specify what this action was. So far, discussion is completely general. We didn't say what the action was. Okay, so let's have a look at this action. So this action If I write it in terms of rho and j, okay, so I don't know what it is, but it has to be of the form. So in imaginary time, it has to be of this following forms, and it's an integral over space-time. If we're at infinite temperature, if we are at 0 temperature, then the imaginary time direction is infinite. But if we are at finite temperature, tau would go, say, from minus beta over 2, right? But let's forget finite temperature for now. But this let's just keep in mind that the imaginary time direction here goes to infinity if we are at 0 temperature. And then there's some function, and we don't need to know exactly what it is. Some function that will depend on rho of x, but rho of x we write in this way above here. So it's the mean value plus some small fluctuation, and then there's the current, which is again of the same order as delta rho. Okay, so this depends on x and tau, and the current depends on x and tau. Okay, so now this is small. Both delta rho and j are small, so you can Taylor expand this thing. So you Taylor expand. So to leading order, this is, you just get that this is f of the mean density and the mean current, which is 0. Then there's a first order term, which looks like this. So it's the, okay, so you pick up the gradient of this function f times the gradient of the height field, something like that, maybe up to some factors 2 pi, but it doesn't matter. And then you get here another factor that looks like this. Times some 2 by 2 matrix here. So this is the Hessian. Here you pick up the Hessian of this function f, multiplied by the two components of the gradient, and then some higher order terms that are of order, and those higher order terms will typically be of order gradient of h to the 3. Okay. Now, this is just a constant, so it's not, we don't care about it. This, do you know what this is? So this is 0. Why is it 0? No. I mean, you should ask that this is 0 because this is the equation of motion, right? This is the equation of motion, so it has to be 0. Otherwise, you know, we are expanding around the minimum, right? The ground state has to be correspond to a minimum of this action. We are assuming that near the ground state we have this. So we are assuming that we are near the ground state. And so this thing has to be 0 because that needs to satisfy the equation of motion. And then we see that the first term that is relevant for us, for our purposes, and to capture the fluctuations, it's this second order term. Okay? And it's this second order term, and we need to look at, okay, so there's this 2 by 2 matrix that has to be symmetric. Now you can easily argue just because of parity. So you have to look at parity. So if the system is invariant when you change x into minus x, or if you want when you change the current to minus the current, you can easily check that these two entries here need to be 0. So it has to be a diagonal matrix. Okay? It has to be a diagonal matrix, and you can take out the determinant. Can take out a factor from this matrix that is the 1 over the determinant of this matrix. So 1 over the determinant of this matrix, you take it out, and you just put it as a global factor here. So so you need to allow for a slightly more general factor here. This slightly more general factor here we write as capital K. And then you are left with 2 coefficients that must be the inverse of each other, lambda and 1 over lambda, say. Okay? But these 2 coefficients, you see, because here you have a derivative with respect to position and derivative with respect to time, this coefficient lambda must be homogeneous to a velocity. And so let's call it V and 1 over V. Okay? So that's the most general thing that can happen. And now if we write, if we just introduce complex coordinates z equals x plus I v tau, if you write this action here in terms of the complex coordinate z equals x plus I v tau, we arrive at the conclusion that our action, the conclusion is that the action that captures the quantum fluctuations, so the effective field theory, the action of our effective field theory must be S equals some constant that we don't care about. That was the 0th order term. Some constant plus 1 over 8 pi k times integral of dzh dz bar h. Okay, let's not write. Let's just write this as this: gradient of h squared in those coordinates times d to z. Okay, so it is this way we find the Gaussian free field. So this is the Gaussian free field. It is the Gaussian free field. There's just a slightly different normalization because of this factor 1 over k. But otherwise, it's really the same as what we have been talking about so far. And okay, k is dimensionless. K is dimensionless. K is dimensionless. It parameterizes. It's a parameter that reflects the strength of the interactions. It parameterizes the strength of the interactions between the particles, strength of interactions in the system. So in particular, this parameter k would depend, I mean, in terms of the original model, it would depend on this two-body interaction v of x minus y. And it has a name, it is called the Luttinger parameter. It's called the Luttinger parameter. And so we see that if we think of how this action appears, there must be such a parameter, a free parameter that shows up. There's another free parameter which is the velocity. So this is the GFF. There's just one important difference with everything we have discussed so far, which is that the number, and this constraint you get from the fact that the number of particles need to be an integer. So the number of particles in the system must be an integer. And so in particular, if you imagine that you have, say, periodic boundary conditions, right? So that the system here, the direction x is compact and that you have the total length L, then what you want is that the field H satisfies that the density, so the total excess of the total excess of the number of particles, so the difference between the number of particles of any configuration in the system with respect to the ground state. This should be given by integrating this so small fluctuation from 0 to L. And this, because delta rho was, this was delta rho, sorry. This is delta rho, because delta rho is 1 over 2 pi times h. Then we see that here we find that this is h of L minus h of 0. And so a natural way to implement this is to ask that h is identified, h is identified with h plus 2 pi. So that's the big difference with what we have discussed so far. It's that the field H in this effective theory, you should think of it as living not being a real number, but being a real number modulo 2 pi. So it's not really the Gaussian free field, it's a compact version or compactified version of the Gaussian free field. Okay, good. So now this is what we conclude. So conclusion is that the effective field theory of these one-dimensional quantum liquids, this is always a Gaussian free field. Conclusion. The effective field theory of those one-dimensional liquids, quantum liquids, this is a Gaussian free field, compactified Gaussian free field. So the field is compactified to, so the field takes values modulo 2 pi, and the action has this form that there's this prefactor 1 over 8 pi k, and k is then an important parameter in the theory, and it enters whenever all correlation functions, all physical quantities that you might want to calculate involve the Luttinger parameter k. Okay, so we are there. That's the effective theory, and now let me just in 3 minutes quickly sketch how you can get these correlation functions that I've been advertising. So the correlation functions do not completely come for free. The reason for this is that there is some work to do to correctly identify the right operator in the field theory that replaces your operator in the microscopic model when you think of the microscopic model, and this is not always obvious, although by playing with general arguments like what are the symmetries or what are the different charges that are carried by the operators, you can usually determine them. But anyway, so for instance, this operator psi dagger in the microscopic model that we have been talking about, it turns out, so this I would need to take some time to discuss, and I don't have this time, so let me just drop the result. It turns out this operator is of the following form, so it's a constant. There's some constant that is dimension full. So it's a dimension full. So it scales as some length to some power. It depends on the microscopic model. on the microscopic details of the system. So this constant in general we don't know, or at least it's not provided by just by the field theory argument. But then it's this constant times an operator in the field theory, and this operator in the field theory we can identify. So it turns out in this case this is given by phi of z minus phi bar of z bar. Recall that we were calling H, the field H, we were decomposing as fields phi and phi bar. Right? Recall that we had this decomposition into a chiral and anti-chiral component of the H field. And also, if you do that, turns out the correct operator is this one. So it is one of these vertex operators that we have been talking about so much. It is of this form. The only difference with the operators that we talked about so far is that there's a minus here between phi and phi bar instead of a plus. But this I mean, if you want to know why this is so, we can discuss this afternoon, maybe in the discussion session. It's important, but I don't have time to discuss it now. And therefore, once you know this, and once you know the effective theory, you can compute all correlation functions you want using the formulas that we have seen many times now. So, for instance, in the ground state on an infinite line, so for the ground state on an infinite line, you know, so you have this and this, your point x1, x2. You want to compute this correlation function, psi dagger x1, psi of x2. Well, so this maps then to a correlation function in the complex plane at two different points, x1, x2, along the real axis, where this direction is imaginary time. And okay, so we know the result. We know the result from lecture 2, and then you find that psi dagger of x1, psi of x2, this is 1 over, or up to this constant a. This is a, then a squared, divided by distance to the 1 over 2k. The 2k comes from here. But now this is, you can go much further than this, so you can do higher points correlations, but you can also do finite temperature. Why can you do finite temperature? So I can do the same setup, but at finite temperature. To make it finite temperature, I need to compactify the imaginary time direction. So instead of computing this on a plane, I compute on a cylinder. The circumference of the cylinder is beta, so 1 over temperature. Beta is 1 over temperature. And you know, then you can map. That's then a correlation function on the infinite cylinder. The infinite cylinder you can map to the complex plane. So using, I think this third exercise that I gave you about this type of correlation functions, you will see that the finite temperature result is this. This is a squared. Again, there's this constant that we do not know, but the rest is completely fixed. It has to be beta over pi, hyperbolic sine of beta over pi over beta times x minus x1 minus times the distance to an exponent, and this exponent has to be the same. So this just follows from conformal mapping from the cylinder, from the plane to the cylinder. And you can do more. You can do finite systems, open boundary conditions. You can do, I mean, you can do whatever you want. These correlation functions are all fixed. So let me just give you one example of the case with boundary conditions. So if you have open boundary conditions, let's say, which corresponds to Dirichlet boundary conditions for H. So this would be then a quantum system with a boundary here and here, let's say of length L. So, okay, and we are interested again in, say, in the 2-point function, x1, x2. So now in imaginary time, this maps to a problem on an infinite strip. This maps to a problem on an infinite strip of width L. So again, you can use a conformal map to the upper half plane, compute, and the result looks like this. Okay, the result looks. I mean, the result is what it is. It's not particularly interesting, but it's good to know that you can get these results essentially for free using conformal mappings. Because if you really start from the system, from the quantum system itself, from the microscopic Hamiltonian, this is totally hopeless. I mean, you will spend the rest of your career trying to compute this correlation function, and you will never get it. But with this effective theory at hand, you get it. You do not get the full result, of course. You do not get the short distance behavior, but as far as the long distance behavior, asymptotic long distance behavior is concerned, you do get it, and you get it easily. It's not much work. So I mean, again, this particular formula is not necessarily super interesting, but it's good to know that it exists in case one day you want to compute correlation functions in the Luttinger liquid on a finite segment or at finite temperature. This is what it is. Okay, and as you know, there are countless applications of the Luttinger liquid. So the point is, you have to be creative to come up with new interesting applications, but the calculations are essentially what we saw in the lecture 2. So that's it. Thank you.
Out of the integral, how do we know that k is independent of h? Because we pulled it out of the integral while writing that equation.